Hi, in this module I'm going to talk about beam search, a really simple algorithm for finding approximate maximum weight assignments efficiently when you're in a hurry and don't want to incur the full cost of backtracking search. So just as to review, remember a constraint satisfaction or a CSP is defined by a factor graph which consists of a set of variables x1 through xn, where each xi can be in some element of a domain I, and a set of factors, f1 through fm, where each factor function, fj, is a function that takes assignment and returns a non-negative number. And usually the factor function depends only on a subset of the variables. So each assignment, little x, to all the variables has a weight, and that weight is given by simply the product of all the factors applied to the assignment. And the objective is to find the maximum weight assignment. So let us revisit the object tracking example. So in this example, we're trying to track an object over time. And at each time step, we record a noisy sensor reading of its position. So at time step 1, we see 0. Time step 2, we see 2. Time step 3, we see 2. And the question is, what was the trajectory that object took? Is it this one or something else? We modeled this problem as a CSP with x1, x2, and x3. We defined factors that captured our intuitions about the problem. O1 captures the fact that the actual position should be close to the sensor reading. So 2 is the weight assigned to 0. So 0, x1 equals 0 is favored, and x1 equals 2 is disallowed. Similarly, O2 favors x2 equals 2, O3 favors x3 equals 2, and finally the transition factors T1 and T2 favor adjacent xi's which are close. So a distance of 0 will get a weight of 2, whereas a distance of 1 will get 1, and so on. Okay, and you can click on this demo to actually play with this CSP. We'll come back to this in a bit. Okay, so this is the object tracking example. So far we've seen backtracking search as a way to compute maximum weight assignments. And backtracking search essentially does an exhaustive depth first search of the entire tree in the worst case, which can take a very, very long time. So how can we avoid this? Well, we have to give up on something, and what we're going to give up on is correctness. So what we're going to do is simply not backtrack. So let's start with something called the greedy search algorithm. So again, we start with the empty assignment. We consider possible settings of, let's say, x1. So let's say there's 2 possible settings. And we're just going to choose one of them, whichever one has the highest weight. And the weight of, remember, of a partial assignment is the product of all the factors that you can evaluate so far. So let's pick with this one. Again, let's set x2. There's 2 possible ways to set it. Let's pick the better one and keep on going until we reach a complete assignment. And then we just return that. So formally, what greedy search is doing is starting with a partial assignment, which is empty, and then it's going through each of the variables x1 through xn. I'm going to try to extend the partial assignment to set xi. So for each possible value that I can assign xi, I'm going to form a potential candidate partial assignment and call it xv. And then I'm going to compute the weight of each of these xv's and then choose the one with the highest weight. So important caveat is this is definitely not guaranteed to find the maximum weight assignment, even though locally it appears to be optimizing and finding the value with the best weight. So let's look at this demo to see how it works on object tracking. Okay, so Here we have the CSP that's defined, and I'm going to step through this algorithm. So initially, I extend the empty assignment to assignments that only fill in x1. So x1 could be 0, 1, or 2. And these are the weights of these three partial assignments. Remember, the sensor reading was 0, so therefore x1 equals 0 has a larger weight. So next step, I prune. I keep only the best candidate, which in this case is x1 equals 0. So then I go to I equals 2, and I extend that assignment to 3 possible settings of x2, compute their weights, and then I keep the best one, which in this case is 1. And now I extend again to x3, 3 possible values to set x3, compute the weights of these complete assignments, and then I choose the best one. So in this case, greedy search ends up with assignment 0, 1, 1 with a weight of 4. And if you remember this example, the best weight assignment have weight 8. So 4 is definitely not the right answer, but it's not 0 either. It found something. Okay, so what's the problem with greedy search is that it's too myopic and only keeps the best candidate, single best candidate. So beam search is just the natural generalization of greedy, where I'm keeping at most k candidates at each level. So let's say k equals 4. So I'm going to start with empty assignment. I'm going to extend. And then I don't need a prune because there's only 2 possible partial assignments here. And I have a capacity of 4. I'm going to extend again. Again, I don't need a prune. But then next, I'm going to extend each of the elements on my beam, the partial assignments. Extend each of these. And now I have 8. And now I need to reduce the 8 partial assignments to 4. And to do this, I'm going to simply compute the weight of each of these 8 partial assignments, and then take the 4 which have the highest weight. And now let's suppose those are these 4, and then I continue only expanding the ones I've kept, and then keeping the ones, again, the top 4, and then keep on going. So notice that visually, I'm exploring only a very, very small fraction of the tree, but I'm doing this kind of holistically, looking down the tree at kind of multiple, I could be exploring different parts of the tree at the same time. So formally, beam search keeps at most k candidates of partial assignments. So I'm going to initialize the candidate set to be just the single partial assignment, which is empty. Now again, like greedy search, I'm going to go through the variables one at a time. I'm going to extend. In this case, I'm going to consider each partial assignment in C and each possible value that I can assign xi. And then I'm going to perform the extend the assignment. And I'm just going to keep track. A C prime is going to be the new set of candidates. And then now I'm going to prune that set by computing the weight for each element of C prime and just keeping the top k elements. Okay, so this is not guaranteed to find the maximum weight assignment either, but sometimes it works better. So let's look at this example. Object tracking, and extend from the empty assignment to get 3 partial assignments to x1. I prune to the top 3, so nothing gets removed. I then extend. So each of these 3 partial assignments gets extended into 3 additional ones. Now I have 9. And now I'm going to prune down from 9 to 3. So that will keep all the assignments here with positive weight. And now I extend again to find settings of x3, compute each of these weights, and then I'm going to take the top assignments. Okay, so now notice that the top assignment that I have right now is 1, 2, 2 with a weight of 8. And in this case, I got lucky and I found actual max weight assignment. But in general, you won't be guaranteed this. Okay, so what is the time complexity of beam search? Because one of the advantages is that it's supposed to be fast. So let's do a simple calculation here. So suppose we have n variables, which is the depth of this tree. And suppose that each of the variables has v elements, which is going to be the branching factor here. And then the beam size is k. Okay, so what is the time that it takes to run beam search? It's going to be for each of the variables, each level of this tree, we're going to have a set of candidates which is of size k. And the extension phase is going to take each of these k and extend it into b candidates. So then I'm going to end up with kb extended candidates total. And then I'm going to have to take the top k. So the time it takes to take a list of kb elements and select the top k elements is kb log k by building a heap. So the total time is n kb log k. And importantly, this is linear in the number of variables, whereas backtracking search would be exponential in the number of variables. Okay, so let us summarize now. So beam search is a fairly simple heuristic to approximate maximum weight assignments. And it's really done if you're really in a hurry and you don't really care about getting maximum weight assignment, because you probably won't. So the nice thing about beam search is it has this parameter k, which allows you to control the trade-off between efficiency and accuracy. So if you're really in a hurry, you set k equals 1, you just get greedy search, which sometimes actually gets you pretty good answers. And if as you increase k more and more, if you increase k to infinity, then you'll definitely search the entire search tree and you will get the optimal answer. But this is basically exponential time. One thing to know about beam search with k equals infinity, it is performing a breadth first search of the tree, because at each it performs level by level and explores all the nodes in the tree kind of systematically. So using this analogy, I want to end with a final note here, which is that backtracking search is really like doing a depth first search on the search tree. It dives deeply into one complete assignment and then backtracks and then finds another complete assignment and backtracks, looking kind of one assignment at a time. Whereas beam search is more akin to breadth first search, where we're proceeding level by level. But the main difference with breadth first search is that we're doing this heuristic pruning at each level to make sure that we don't have too many candidates. And the way it's doing that pruning is based on the factors that it can evaluate so far. So for beam search to work, you really need it to be the case that the factors are local and they can be evaluated as much as possible along the way and not all at the very end. All right, so that's the end of this module.